In this video, I'm focused on balanced forces, unbalanced forces, and net force. This is the third of 7 videos in my Unit 3, titled Dynamics in One Dimension. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 3.03, as well as video answers for each problem. When it comes to analyzing the motion of an object in a straight line, there are 4 things that the object can do. I'm going to group the first 2 together, as they show an object that is not changing velocity, whether that is always 0 or always some constant number. These objects are not accelerating. I'll group the final 2 together, because these represent objects that are changing their velocity or are accelerating. For the first 2 motions, where there is no acceleration, that would be a sign that the forces acting on the object are balanced. You would want to draw equal vector lengths in your force diagram, and your equation that connects to the diagram should also state that forces are equal in magnitude. Many students remember to use balanced forces when the object is at rest, but many students forget to also use balanced forces when the object moves with constant velocity. For the other 2 motions, where the object is accelerating, this would connect to unbalanced forces. Notice that the force diagram shows unequal vector lengths, and the statement that connects to the diagram states the same mathematically. Let's look at a few examples. The goal for each of them will be to draw a proper force diagram and then analyze forces as being balanced or unbalanced. The first example is here. We have a lamp sitting motionless on a dresser. My object is the lamp. There are 2 forces acting on the lamp, a downward force of gravity from Earth and an upward normal force from the dresser. While this lamp is at rest, it is motionless in each dimension, so forces should be balanced in each dimension. Left and right, there are no forces, so 0 equals 0, no equation is necessary, but vertically, the normal force is balanced with the gravitational force to explain why the object is not moving up or down. Here is example 2. We have a man using a rope to pull a box across a grass surface. The box is stated to slide with a constant velocity, so the focus is on the box. There are 4 forces acting: a downward force of gravity from Earth, an upward normal force from the surface. Kinetic friction would act back to the left, resisting the motion to the right, and the tension force is angled, caused by the angled rope. Because one of the forces is angled, and there is no angled ramp, I will break that angled force up into its components, x to the right and y vertically upward. And now I consider what the object is doing in each dimension. Well, it has a constant velocity in the horizontal plane, and it is motionless in the vertical plane. These are both statements of balanced forces. So horizontally, I want to state that kinetic friction is equal to the x component of tension. And vertically, I want to state that the 2 upward forces, normal force and tension's y component, when added together, they are balanced with the downward gravitational force. Many students believe that if an object is moving to the right, then the force to the right is automatically larger. Well, be careful. That is an incorrect statement. It depends on which motion type the object has, and if it is a constant velocity, then the forces are equal in magnitude. Here is the next example. We have a weightlifter accelerating a bar upwards. The focus is on the bar, and there are 2 forces acting: an upward pushing force from the person and a downward gravitational force from Earth. Well, this bar is motionless in the horizontal plane, and that would make sense because there are no horizontal forces acting, so there is no equation necessary. But vertically, the object is accelerating upward, meaning that it is speeding up, and the only way that would be true is if the pushing force is larger in magnitude than the gravitational force. So I'm showing that with the vector diagram and stating as much with this unbalanced force equation. One final example is here. We have a box that is slowing down as it moves to the right along this rough surface. The focus is on the box, and there are 3 forces that act: a downward gravitational force, an upward normal force, and a kinetic frictional force directed to the left, opposite to the velocity and parallel to the surface. In the vertical plane, the object is motionless, so the normal force is balanced with the gravitational force, and I'm showing that in both the diagram and the equation. Horizontally, though, the object is slowing down and accelerating, so forces should be unbalanced. Well, here I have a force to the left and no force to the right, and that is why the object is slowing down. Many students believe that if an object is moving to the right, then there must be a force acting on the object that is directed to the right. Well, be careful. Nothing is stated in this problem affecting the object in that direction, and there's nothing in the picture as well. Whatever made the object move to the right in the first place has now lost contact with the object, and that's why the object is slowing down, because it is moving to the right with a force to the left. Next, let's focus on net force. This is the summation of all forces acting on an object. Some teachers use the F subscript net variable, and other teachers use the sigma F variable to describe net force. Know that the sigma variable in math means summation, so these two variable options are saying the same thing, as a net force is the summation of forces, so figure out what your teacher prefers and go with that. Well, how do we solve for a net force? Here is a first example. We have two forces simultaneously acting on an object. There's a 3 Newton force acting to the left and a 5 Newton force acting to the right. Of the 5 answer options, which of them represent the net force acting on the object? Well, it would not be choices B or C. The net force accounts for all of the forces acting in this horizontal plane and not just one of them. It would not be choice A, as this would say that we want to add the force magnitudes together, and that would only be true if they acted in the same direction. I think the answer is choice D, 2 newtons, because I want to subtract these forces in opposite directions, and the net force should be directed towards the side with the greater force. The spot that you'll commonly be in is not with numbers, you will be doing it with concepts. And maybe we have already determined that forces are unbalanced on an object, and the tension force is greater in magnitude than a kinetic frictional force, as shown in the image. Well, which of these equation options would represent the net force acting on the object? I think the answer is choice A. It considers both forces and not just one of the forces, like choices D and E. It considers direction by subtracting the forces, unlike choice C that adds them together. And by leading with tension force, that is stating that the tension force is larger in magnitude and that the net force is directed in the same direction as the larger force. So for any situation where you have more total force acting in one direction than in the opposite direction, you will want to write a net force equation. You will want to subtract your oppositely directed forces, and I recommend that you lead your subtraction with whatever direction has the greater amount of force. Doing it this way will set the direction with more force as the positive direction, and that way you will always get a positive value for net force. You will always get a positive acceleration, and negative numbers will not be necessary. Here are 3 quick examples. We are trying to take these diagrams and turn them into net force statements. The first one states that tension and kinetic friction are equal in size and opposite in direction. Well, I might consider subtracting them, but they have the same magnitude, so they would subtract to 0. There is no net force when forces are balanced. The middle example, we now have tension and kinetic friction acting in the same direction. We can certainly add forces together in a net force equation if the forces are directed the same way. The last example shows a tension force that acts alone. There is nothing to compare this force with, whether adding to it or subtracting from it. Whenever you see a force that acts alone in a dimension, then make that force the net force. Here is a summary of what has been discussed so far as it relates to writing net force equations. The first thing you want to look for is the type of motion that the object has. If it is motionless, or if it moves with a constant velocity, that means it is not accelerating. That means forces acting on the object are balanced, and that means there is no net force. If instead the object is speeding up or slowing down, now it is accelerating, that means forces are unbalanced, and that means you will have to write a net force equation. Let's end with an example problem. Here we have a crate speeding up as it is pushed to the right across a rough surface. The goal is to complete a force diagram and write the connected force equations for the crate. If you want to pause the video and try this problem on your own, resume when you are ready, and I will walk you through the solution. I start with identifying my object as the crate. There are 4 forces acting on the crate: a downward gravitational force, an upward normal force, a rightward pushing force from the person, and because the object is in motion along the rough surface, there would be a kinetic frictional force acting back to the left. From there, my force equations, I am considering what motion types the object has. In the vertical plane, the object is motionless, and in the horizontal plane, the object is accelerating and speeding up to the right. So vertically, I would state balanced forces, Fn is equal to Fg. Horizontally, the pushing force is larger than kinetic friction. I'm showing that in the diagram, and I'm writing a net force equation with the larger pushing force subtracting the smaller kinetic friction force. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.